In statistics and probability, one of the most important distributions is called the Gaussian distribution, or sometimes called the bell curve, or really the normal distribution. And the reason this is called the normal distribution is because it occurs very frequently in the statistical sciences. Applies in machine learning. It's often assumed type of distribution for a continuous random variable, and even when it's not, there's something called the central limit theorem, which describes how any distribution, if we sample from it, when we collect all these means from our samples and we plot them, we get something that looks Gaussian in nature. So Gaussian, bell curve, normal distribution, all referring to the same thing. As most distributions are, the Gaussian distribution is fully based upon specifying two quantities, and those are the mean and the standard deviation, which I should say here, or I should say the variance. But we can go ahead and specify that as the standard deviation, which is just the square root of the variance. Now remember, the mean specifies a measure of central tendency. If all the values were the same, that would be what the mean represents. And the standard deviation is the square rooted variance, which describes kind of the average amount of spread. And the PDF, the probability density function, is given by this function here. Now, I want to explain this for a moment. Here we have a random variable. So depending on what value x is, will determine what the density at that location is. And it depends upon two things that are given. Okay, remember, this means given that, and these are the quantities that we need to know. Those are the givens. And so given a mu and a sigma, then we can actually plot the probability density function. And it's this sort of big looking function. It's this coefficient, 1 over the square root of 2 pi sigma squared, e raised to the negative of x minus mu squared divided by 2 sigma squared. Now, once again, mu and sigma are the quantities that get plugged in, so you could really simplify this quite a bit. And this is defined on a domain from negative infinity to infinity. As we get closer to negative infinity or closer to positive, in the direction of positive infinity, then our distribution essentially becomes 0. So if we were to think about this as the x-axis, then we might have in our bell curve, this is what a bell curve often looks like, and this really decays rapidly down to 0, and the majority of our distribution, kind of falls between two reasonable values of x. Now, it's really customary, you'll see this a lot in practice, rather than writing e to this power right here, which is fine, it's just kind of hard to tell that this is a power and it's, that it's not subtraction. You'll see a lot of times in mathematics, we just say exp, and exp, this means e to the power of, and then whatever comes after that. In this case, this is just e to that power, which is the same thing on the left. Now, mu specifies the horizontal position of the maximum. So the maximum of the bell curve occurs at x equals mu. And just to illustrate what mu does, suppose that sigma is equal to 1 for simplicity. So it's basically, we're going to look at 3 curves all with the same spread. So all these curves look identical except they are shifted. So the red curve actually represents, well, if you looked at this and said, at what value of x does the max occur? Well, it appears that this would be for an x value of 0, and the peak occurs at x equals mu, so that means this would be mean 0. Now for the blue curve, we look at where that appears. It appears that that is at about x equals 3. So this is the curve with mu equals 3, all with sigma equal to 1. It's the same amount of spread in all 3 curves, and that's why they look the same. They're just really horizontal shifts, and this would be for mu equals 6. Okay, so it's this point, and this point. These are just plotted on the same set of axes just for comparison. And to really drive this home, let's take a look at this graph. So I can here I just have I'm calling the function normal dist that actually accesses the PDF just so I don't have to type in 1 over the square root. This just does it automatically. And you can see all that value of mu does is it causes a horizontal shift. Now, if you look at this function and you're like, okay, why? Why does it do that? Well, remember that if you think about transformations in algebra, whatever quantity we add or subtract from x, and notice that that's the only place where mu appears, like if I plotted x minus 3 quantities squared, that would just be the parabola x squared shifted to the right 3 units. Why is it shifted to the right if it's a minus? Well, that's because when you plug in x equals 3, you get 0. So you have to have a bigger value of x to get the same output from this function. So in x squared, of course, you would just plug in x equals 0 and you get 0 squared. But here in this expression, you would need to plug in x equals 3 to get 0 squared. So it's a shift to the right if it's subtraction, shift to the left if it's addition. So that's the simple answer there. Don't let this function intimidate you. There's a lot of stuff that goes into it, but this is just a constant, just a coefficient. And then up here, is sort of where most of that magic happens. So that's the mean. The mean just, is a shift. And what happens if we vary the sigma and keep the mu fixed? So notice that all of these have mu equal to 3. They're all peaked at the same value of x. The only difference is the amount of spread. And what we do know is that as sigma gets bigger, that means there is more spread. And so we would say that of these, the purple one has the least amount of spread, and that is actually for sigma of a spread of 1. Okay, so I'll uncheck this and I'll use this other one. There's our spread of 1, and you can actually see, here's what would happen if you had a spread of 2 units, and that's exactly this second one. This is for sigma equal to 2, and this one is for sigma equal to 3. So you see that we get flatter peaks, and we just get more horizontal. We get more horizontal spread. Now remember that the area under the normal curve, if you were to integrate f of x from negative infinity to infinity dx on all of these, you would get 1, because although it's a density, the reason, if we have more spread, we need a lower peak in order to maintain the same area. To see why this happens, a little bit more complicated, but because of the fact that sigma appears in multiple locations, as sigma gets bigger, this coefficient gets smaller, so that's going to be a smaller vertical stretch. And then because here we are dividing by it, it'll also give us a little bit slower decay in the curve to the right of the peak and the curve to the left of the peak. So the sigma just spreads things out. Okay, if you had sigma equals 100, you would just get something that looks, pretty flat, but a tiny peak. And you can see that as the standard deviation gets bigger, there's more area to accumulate before you really sort of zero out on the y value. So that's pretty much how we work with distributions, and that's just the basics of them. Okay, here's just, looking at a bigger standard deviation. You can once again see that, it's just more spread. And in any case, the integral, the area under the curve is going to equal 1. So this could actually happen in the multivariate realm. Let's say we have multiple random variables and they each follow a normal distribution. We would say independent and identically distributed. So we'll also take a look at what that distribution would look like when we have a collection of means and a collection of variances and covariances.